The circuit below begins with the switch open. The resistor has a value of 2 kiloohms, the inductor is 3 millihenries, and the battery is 8 volts. At time t equals 0, the switch is closed. Answer all the following. We'll solve our transient response problem by identifying the time constant and then reasoning the shapes of the saturating exponential or falling exponential curves. For an LR circuit, we recognize that the time constant is L divided by R, and in this case that will be 3 millihenries divided by 2 kiloohms. 3 over 2 is 1.5, and milli divided by kilo is micro, and so the time constant of our circuit is 1.5 microseconds. In order to solve this problem by reasoning, we recognize that there is a resistor whose voltage is equal to current times resistance, and there's also an inductor, and the inductor's voltage is minus the time derivative of current times the inductance L. The second of these equations I hope you recognize as the voltage on an inductor opposes the minus sign, the change in the derivative current through the inductor. The inductance L is the proportionality constant between amps per second and volts. We recognize in these two equations that L and R are constants, and this means that the quantities we would wish to plot are the voltages on the resistor and inductor and the current. It would be redundant to plot both the current and its time derivative, and so we're only going to plot the current as a function of time. The inductor will be on the right and the resistor will be on the left. We recognize that the role of an inductor is to oppose a change in current. And so at the moment that the switch is closed, the inductor will do whatever is necessary to ensure that there is no current whatsoever flowing through the circuit. That is how it maintains the status quo of zero current flow. If there is no current flow in the circuit, then V equals IR for the resistor, so the voltage on the resistor is also zero. Because the resistor and inductor are in series, the sum of their voltages must add up to that of the battery, and so this means that the inductor's requirement to maintain zero current is that it produces the full 8 volts. We understand that the opposition of the inductor will have a time constant, and so this opposition, initially 8 volts, will decay away to 0. As the inductor goes from 8 volts to 0 volts, the resistor will go the other way around, since they must sum to a constant 8, and at long times the resistor's voltage will saturate to 8 volts. Finally, since V equals IR for a resistor, the current will be proportional to the voltage, and therefore, since the voltage is a saturating exponential, so is the current. To get the asymptotic value, we recognize that V equals IR, so that the current at this point is going to be 8 volts divided by 2 kiloohms. 8 over 2 is 4, and 1 over kilo is milli. In order to write the three equations for part C of the problem, we simply need to identify whether each curve is a saturating or a falling exponential, and then select the appropriate constants. The resistor has saturating exponentials for its voltage and current, and the inductor has a falling exponential for its voltage. Both of the voltage equations have an amplitude of 8 volts, and the current has an amplitude of 4 milliamps. Finally, we're asked at what time does the voltage on the inductor reach 3 volts, and in order to figure that out, we're going to need an equation that links the voltage on the inductor to the time t, and that one is given here. So plugging in the 3 volts into this formula, we're able to solve for the time required, which is going to be negative the time constant tau times the natural log of 3/8. Note, please, that 3/8 is about 37%, and that is very close to the condition of one time constant. Therefore, it's no surprise when we plug in the numbers that this time will be equal to 1.47 microseconds, which is extremely close to being the time tau. And that ends our analysis of closing the switch in an LR circuit. Please note that we won't solve the problem of opening the switch in an LR circuit. What happens, in fact, is very interesting. The inductor will attempt to cause the current to continue to flow, and as a result, it will make a spark across the switch, and this is the mechanism by which a spark is created in an internal combustion engine like in your car.